The technical team arrived at dawn. 6 engineers from McCoy's intelligence unit circled the captured Betty like surgeons examining a patient who'd survived against impossible odds. Cameras ready, notebooks open, measuring tools laid out on the tarmac. The bomber sat silent in the morning heat, intact, operational, statistically impossible. "How many combat missions did this one fly?" Lieutenant Robert Chen asked, running his hand along the fuselage. McCoy checked his preliminary notes. "Records we captured suggest at least 40 sorties, maybe more." Chen's hand stopped. 40 missions? In this? It was a fair question. By January 1945, Betty bombers were legendary for their vulnerability. Fighter pilots across the Pacific had been shooting them down for 3 years with a consistency that bordered on routine. 2 or 3 hits anywhere along the fuselage, instant fireball. A short burst into the wings, catastrophic explosion. The loss statistics were brutal. At Guadalcanal in August 1942, 18 of 23 shot down in a single engagement. At Rabaul throughout 1943, entire squadrons decimated. Over the Philippines in late 1944, formation after formation reduced to burning wreckage before reaching their targets. The Betty earned its nicknames honestly: Flying Cigar, One-Shot Lighter, Flying Zippo. Yet somehow, this particular aircraft had survived 40 missions. "Check the combat damage," McCoy ordered. The team moved methodically along both sides of the fuselage. Minor flak damage near the tail, patched with aluminum sheet. A few bullet holes in the vertical stabilizer, sealed but not replaced. Some stress cracks around the bomb bay, typical wear. Nothing catastrophic, nothing that explained how this bomber had survived when thousands of others hadn't. "Engine covers," McCoy said. 2 engineers climbed onto the wings and began removing the cowling panels from the starboard radial engine. The 14-cylinder Mitsubishi G4M appeared well-maintained despite obvious field repairs. Oil lines showed proper care, spark plugs recently changed. Maintenance logs discovered in the cockpit indicated Japanese ground crews had kept the aircraft operational under increasingly desperate conditions. But maintenance couldn't explain survival. "Major, you need to see this." Chen's voice came from inside the port wing, where he'd opened an inspection panel. McCoy climbed up. Ducking through the narrow access hatch into the wing's interior cavity, Chen's flashlight illuminated the fuel system, or rather, the absence of protection around it. Fuel lines ran exposed along the wing's structural ribs. The tanks themselves, massive bladders containing hundreds of gallons, were wrapped in nothing but thin aluminum skin. No rubber coating, no protective layer, no armor plating. McCoy had suspected this since the preliminary inspection, but seeing it confirmed, documented, undeniable, it still shocked him. "Every hit should have been fatal," Chen whispered. "Every single hit." McCoy's flashlight traced the fuel lines from root to tip. Miles of vulnerable plumbing, thousands of liters of high-octane fuel, protected by aluminum thinner than a mess kit plate. "How did this survive 40 missions?" Chen asked again. McCoy understood the real question. How had any Betty survived long enough to accumulate combat experience? Before we continue, click that subscribe button, like this video, and let me know in the comments where you're watching from. It brings me great joy knowing that these war stories and lessons get to people all over the world. Your support helps us bring more thrilling war stories, and trust me, you won't want to miss them. Now, let's get back to the story. The answer would require understanding not just engineering, but philosophy. Japan had built a bomber that could reach impossible distances by accepting impossible risk. "Let's document everything," McCoy said quietly. "Every line, every tank, every deliberate choice." Because this wasn't about one lucky aircraft. This was about an entire nation's approach to air warfare, and understanding why that approach had failed. December 1941 through June 1942. The Betty bomber dominated the Pacific theater for one simple reason. No Allied fighter could touch it. Range was everything in those early months. While American B-17s struggled to reach targets 500 miles away with meaningful bomb loads, Betty formations routinely struck from bases 700, 900, even 1,200 miles distant. The asymmetry was devastating. At Rabaul, Japanese commanders could hit targets across the entire Solomon Islands chain without moving their bombers forward. At Formosa, they could strike the Philippines repeatedly while remaining beyond American retaliation. At bases throughout the Dutch East Indies, they could attack Darwin, Australia, 1,500 miles away, with impunity. Allied fighter defenses were irrelevant when they couldn't reach the enemy's departure airfields. Captain James Wiggins, flying P-40s from Port Moresby in early 1942, described the tactical frustration. "We'd get the air raid warning, scramble, climb to altitude. Sometimes we'd see them. Perfect V formations at 20,000 feet, completely beyond our intercept ceiling. We'd watch them drop their bombs and turn north. By the time we reached combat altitude, they were 50 miles away and accelerating. We never got close enough to fire." The Betty's operational radius exceeded 1,500 nautical miles with standard bomb load. American fighters like the P-40 Warhawk had combat radius under 400 miles. Even the vaunted P-38 Lightning, when it finally arrived in theater, couldn't match the Betty's endurance. This range advantage translated into strategic flexibility that Allied commanders couldn't counter. When MacArthur's forces occupied Buna on New Guinea's north coast, Japanese bombers simply struck from Rabaul, 560 miles away. When Allied fighters deployed forward to intercept, Betty formations shifted their approach routes or struck different targets entirely. The vast distances of the Pacific theater gave Japanese aviation nearly unlimited options for avoiding interception. Throughout the Dutch East Indies campaign, Betty bombers operated with near impunity. They struck Surabaya from bases on Borneo. They hit Singapore from airfields in Indochina. They attacked Allied shipping throughout the South China Sea, from positions that remained beyond Allied bomber range for months. The aircraft's success rate during this period was extraordinary. Formations routinely completed missions without encountering enemy fighters. Anti-aircraft fire proved largely ineffective against bombers operating at 18,000 to 22,000 feet. Betty crews accumulated combat experience rapidly, refining their tactics while Allied defenses struggled to adapt. Japanese naval aviation commanders praised the G4M as vindication of their pre-war doctrine. The bomber's range enabled the kind of offensive operations that transformed Pacific geography from an obstacle into an advantage. Island bases became unsinkable aircraft carriers. Ocean expanses became defensive barriers that protected Japanese bombers while exposing Allied positions. But this dominance rested on a single assumption, that Allied fighters would remain unable to intercept Betty formations in meaningful numbers. That assumption would hold for exactly 6 months. By mid-1942, American industrial capacity began delivering new fighters to Pacific bases. Wildcats gave way to Hellcats. P-40s were supplemented by Corsairs and improved P-38s. Pilot training improved. Tactics evolved, and the moment Allied fighters could reach Betty formations in strength, the bomber's fundamental vulnerability would be exposed. The aircraft that seemed invincible in December 1941 would become a death trap by August 1942. The difference wasn't Japanese tactics. It was American fighters finally getting close enough to shoot. December 10th, 1941. South China Sea, off the coast of Malaya. The battleship HMS Prince of Wales and the battlecruiser HMS Repulse steamed northward without air cover. Force Z, as the Royal Navy designated the task force, represented Britain's attempt to project naval power into Asian waters. Prince of Wales alone displaced 43,000 tons, one of the newest, most powerful battleships afloat. Admiral Tom Phillips commanded from Prince of Wales's bridge, confident that capital ships could defend themselves against air attack through maneuver and anti-aircraft fire. Naval doctrine still held that battleships remained supreme. Aircraft were a nuisance, not a mortal threat. The Japanese Navy disagreed. At approximately 11:15 a.m., 26 G4M Betty bombers departed from airfields near Saigon in Indochina. Another group of older G3M Nell bombers joined the strike. Their target, Force Z. Detected by reconnaissance aircraft, 140 miles off the Malayan coast, the bombers carried Type 91 aerial torpedoes, 840 kilograms each, with 205-kilogram warheads designed specifically for shallow water operations. The torpedoes could run at depths that allowed them to strike even in coastal waters, negating one traditional advantage of maneuvering capital ships. First contact came at 12:20 p.m. The Betty formations approached in coordinated waves, their attack profiles executed with precision that stunned British observers. High-altitude level bombers struck first, forcing the capital ships into evasive maneuvers. Then torpedo bombers came in low, 50 feet above the water, launching from multiple directions simultaneously. Prince of Wales opened fire with every anti-aircraft gun. The battleship's defensive armament was formidable. Multiple 5.25-inch dual-purpose guns, numerous smaller caliber weapons, the latest fire control systems. Gunners tracked targets, adjusted lead angles, poured shells into the sky. Several Japanese aircraft fell, trailing smoke and fire. But the coordinated torpedo runs couldn't be stopped. The first torpedo struck Prince of Wales amidships, then another and another. Underwater explosions ripped massive holes in the battleship's hull, flooding overwhelmed damage control efforts. The ship's list increased steadily. Repulse, a battlecruiser modernized in the 1930s but fundamentally a World War I design, maneuvered desperately. Her captain executed every evasive technique in the Royal Navy's playbook. For nearly an hour, the ship dodged torpedo after torpedo through violent turns and speed changes. Then 4 torpedoes found their mark in rapid succession. The cumulative damage proved catastrophic. Prince of Wales capsized at approximately 1:20 p.m. Repulse followed 13 minutes later. Both ships went down in water shallow enough that their superstructures remained partially visible above the surface. 841 British sailors died. Survivors clung to wreckage until escorting destroyers could rescue them. The engagement lasted less than 2 hours from first contact to final sinking. For the first time in naval history, capital ships actively defending themselves had been sunk solely by aircraft while operating in open water. No enemy surface vessels participated. No submarines delivered the killing blows. Just aircraft and the weapons they carried. The Betty bomber had achieved what naval theorists had debated for 2 decades. British naval superiority in Asian waters was shattered in 90 minutes. Across the Pacific theater, Allied commanders absorbed the implications. If modern battleships couldn't survive determined air attack, what could? The Betty's reach, striking from bases hundreds of miles away, combined with its torpedo capability, made every Allied naval formation vulnerable. What those commanders didn't know, what they couldn't see from their sinking ships, was how fragile the aircraft actually were. The Bettys that struck Force Z departed untouched because British fighters never arrived. Had even a handful of hurricanes or buffaloes intercepted the formation, the outcome might have been very different. But that lesson would take months to learn. Mitsubishi Heavy Industries, Nagoya, 1937 to 1939. The Imperial Japanese Navy's specification was unambiguous. Deliver a land-based attack bomber with operational range exceeding 3,700 kilometers. Carry 800 kilograms of bombs or 1 torpedo. Maintain cruise speed above 350 kilometers per hour. Enter service by 1940. Chief designer Kiro Honjo studied the requirements with growing concern. The performance envelope demanded contradicted every principle of conventional bomber design. Range required fuel. Fuel added weight. Weight required larger engines. Larger engines consumed more fuel. The mathematics spiraled into impossibility unless something fundamental changed. Honjo's team ran the calculations repeatedly. A bomber, meeting the Navy's range specification while incorporating standard protective systems, self-sealing fuel tanks, armor plating, redundant structure, would exceed maximum takeoff weight by nearly 2,000 kilograms. The aircraft couldn't fly. Something had to be eliminated. The engineering meetings grew heated. Younger designers argued for reducing range requirements. Senior naval liaisons refused. The Navy's strategic doctrine depended on projecting air power across vast Pacific distances. Range was non-negotiable. Then we must reconsider protection, Honjo said finally. The room went silent. Self-sealing fuel tanks, introduced by American and British designers in the late 1930s, used layered rubber compounds that swelled when exposed to fuel, automatically sealing bullet holes. The technology was proven, effective, and standard on every modern military aircraft in Western arsenals. It also added approximately 500 kilograms to a typical bomber's empty weight. Armor plating for crew positions, engine firewalls, and critical components added another 400 kilograms. Redundant structural elements, fire suppression systems, and protective equipment pushed the total penalty past 1,000 kilograms. Honjo's proposal was radical. Eliminate all of it. Standard fuel tanks, minimal armor, streamlined structure. We buy range with weight savings. Naval liaison. Captain Takahashi considered the implications. Crew survivability? Speed and altitude will provide protection, Honjo replied. The aircraft will operate beyond enemy fighter range. High-altitude bombing runs will avoid anti-aircraft fire. By the time enemy fighters can intercept, our bombers will have departed. The assumption seemed reasonable in 1938. Japan's most likely opponents, the United States, Britain, the Netherlands, maintained limited fighter forces in Asia. Their aircraft had short range and modest performance. A bomber cruising at 370 kilometers per hour at 20,000 feet would be difficult to intercept. The Navy accepted the trade. In April 1939, the first G4M prototype flew. Performance exceeded expectations. Range with standard bomb load, 6,033 kilometers. Maximum speed, 428 kilometers per hour. Service ceiling, 8,950 meters. The numbers were extraordinary, unmatched by any bomber in any air force worldwide. Test pilots praised the aircraft's handling. Naval commanders celebrated its strategic reach. Production orders accelerated, but combat testing revealed troubling vulnerabilities. During operations over China in 1941, G4M bombers occasionally encountered Chinese-American volunteer group fighters. Several bombers caught fire from minimal battle damage. Crews reported fuel fires spreading rapidly through unprotected tank systems. Mitsubishi engineers noted the reports, but recommended no design changes. The Navy concurred. The aircraft's range remained the priority. Protection systems would add weight the design couldn't accommodate. Captain Takahashi summarized the official position in a 1941 memo. The G4M's operational advantages, range, speed, payload, justify accepting increased vulnerability. Our doctrine emphasizes offensive initiative. Enemy fighters will have limited opportunities for interception. The assumption held for 6 months. Then Allied fighter strength in the Pacific began increasing, and the design trade Honjo's team made in 1938, range purchased with crew survival, became a death sentence. August 8, 1942. Skies over Savo Island, Solomon Islands. 23 G4M Betty bombers from the 4th Air Group departed Rabaul at dawn. Their target, American positions on Guadalcanal, where Marines had landed 2 days earlier, seizing the partially completed Japanese airfield. The formation flew at 18,000 feet in perfect V pattern, the same tactical approach that had worked flawlessly for 8 months. Commander Tadashi Nakajima led from the formation's point position, confident in his crew's experience and his aircraft's proven capabilities. What Nakajima didn't know, American radar on Guadalcanal had detected his formation 43 miles out. What he couldn't anticipate, F-4F Wildcat fighters were already climbing to intercept altitude. At 1:15 p.m., 19 Wildcats from Marine Fighting Squadron 223 reached attack position. Captain Marion Carl spotted the Betty formation first, unmistakable silhouettes against white clouds, maintaining rigid formation discipline. "Tally-ho," Carl transmitted. 2-3 bombers, Angels 18, heading 150. The Wildcats dove from 22,000 feet. The first pass shattered the formation's left flank. Carl's guns raked a Betty from nose to tail, a 3-second burst, perhaps 60 rounds total. The bomber exploded instantly. Not caught fire, not trailed smoke. Exploded. A massive orange fireball that consumed the entire aircraft in less than 2 seconds. "Jesus Christ," Carl's wingman radioed. "Did you see that?" Carl had already pulled up for another pass. The Betty formation was disintegrating. Bombers broke left and right, abandoning their attack run, jettisoning bombs early to gain speed. It didn't matter. Lieutenant Kenneth Fraser targeted a Betty attempting to flee northward. His .50 caliber rounds stitched the bomber's right wing. Fuel ignited immediately, a tongue of flame that spread along the entire wing surface in seconds. The aircraft rolled inverted and fell, trailing a comet tail of fire. All across the engagement zone, Bettys were burning. A single burst into the fuselage, instant fire. A short pass along the wing, catastrophic fuel explosion. Even glancing hits produced flames that spread with terrifying speed. The Japanese bombers' defensive guns returned fire desperately. Several Wildcats took hits. But the American fighters pressed their attacks with growing confidence as they recognized the enemy's vulnerability. Commander Nakajima's bomber absorbed hits from multiple attackers. Fuel tanks in both wings ruptured simultaneously. Fire engulfed the aircraft before he could give bailout orders. The Betty fell into the sea off Savo Island with all 9 crew members still aboard. The engagement lasted 17 minutes. 18 of 23 Betty bombers were shot down. Approximately 120 Japanese aviators died. An entire air group's worth of experienced crews lost in a single afternoon. The 5 surviving bombers limped back to Rabaul, several trailing smoke, all carrying wounded crew members. Their combat reports stunned Japanese commanders. Losses of this magnitude were unprecedented, catastrophic, unsustainable. Captain Carl landed at Henderson Field, the newly renamed Guadalcanal airstrip, and climbed from his cockpit, visibly shaken despite the victory. "They just burn," he told the intelligence officer. "Touch them anywhere and they go up like torches. Wings, fuselage, doesn't matter. 2, 3 hits maximum and they're fireballs." The nickname spread through American squadrons within days: Flying Cigar, One-Shot Lighter, Flying Zippo. Grim humor masking a tactical reality. The Betty bombers' mythical invincibility built on 8 months of operations against inadequate fighter opposition, had been destroyed in 17 minutes over Guadalcanal. The aircraft's fundamental design flaw was now undeniable, and the war had 3 more years to run. November 1942. Buna, Papua New Guinea. Australian infantry overran the Japanese airfield at Buna after weeks of brutal fighting. Among the abandoned equipment, intelligence officers discovered what every Allied commander in the Pacific had been requesting for months: intact enemy aircraft. 3 Betty bombers sat on the damaged runway. One had obvious battle damage, wings shredded, fuselage holed. But 2 appeared relatively intact, abandoned by retreating Japanese forces who lacked time to destroy them properly. Flight Lieutenant David Richardson, an aeronautical engineer attached to the Allied Technical Air Intelligence Unit, arrived 2 days after the base fell. He'd examined crashed Japanese aircraft before, mostly fighters pulled from jungle crash sites, their structures twisted beyond useful analysis. These bombers were different. Richardson approached the least damaged Betty cautiously, checking for booby traps before climbing onto the wing. The inspection panels opened easily. Standard fasteners, no unusual security measures. He shone his flashlight into the wing cavity and stopped. "Harper, come look at this." Sergeant Thomas Harper, a former aircraft mechanic from Melbourne, climbed up beside him. Richardson directed the light along the internal structure. "Where's the bladder?" Harper asked. "There isn't one." They moved to the next inspection panel. Same result. Then, the next. Along the entire wingspan, nearly 25 meters, they found identical construction: bare aluminum fuel tanks with no protective coating, no rubber sealant layer, no self-sealing compound of any kind. "This cannot be standard," Richardson said. "Check the other aircraft." Harper and 2 other technicians spent the afternoon examining all 3 bombers. Every fuel system showed identical characteristics: thin aluminum construction, exposed fuel lines running along structural ribs, no armor plating around tanks or feed systems, no fire suppression equipment, no redundant pumps or protected distribution networks. Richardson photographed everything, his documentation growing more detailed as the implications became clear. By 1942, self-sealing fuel tanks were standard on every combat aircraft in British, American, and even Soviet service. The technology wasn't exotic. Layered rubber compounds that swelled when exposed to fuel, automatically sealing punctures from bullets or shell fragments. The system added weight, but the survivability benefits were considered essential. American bombers universally incorporated self-sealing tanks. The B-17 Flying Fortress had featured them since the C model in 1940. The B-24 Liberator included them from initial production. Even single-engine fighters like the P-40 and P-47 carried protected fuel systems. Yet here was Japan's primary long-range bomber, produced in thousands, operating across the entire Pacific theater, with fuel protection that would have been inadequate on a 1930s civilian aircraft. Richardson's preliminary report, transmitted to MacArthur's headquarters 3 days later, stated the findings in stark terms. The G4M fuel system offers 0 protection against battle damage. Any projectile penetrating the wing or fuselage has high probability of igniting fuel. The design appears to deliberately sacrifice crew survivability for weight savings. The response from higher command questioned whether Richardson had examined prototype or experimental aircraft rather than standard production models. Richardson sent photographs. The reply came back within hours. Examine more examples, confirm findings, document everything. Over the following weeks, as Allied forces captured additional Japanese airfields, technical air intelligence units inspected every Betty they could access. Crashed aircraft at Dobadura, abandoned bombers at Lae. Shot-down examples scattered across New Guinea's coast. Every single aircraft showed identical fuel system design. This wasn't experimental. This wasn't a field modification or wartime expedient. This was deliberate Japanese engineering doctrine. Wing Commander Jeffrey Stevenson, Richardson's superior officer, summarized the discovery in a classified memo to Allied air commanders. The enemy has fielded a bomber entirely without modern fuel protection. This explains combat loss rates and validates pilot reports of catastrophic fire vulnerability. Japanese design philosophy prioritizes range over survivability to a degree unprecedented in modern military aviation. The tactical implications were distributed throughout Allied fighter squadrons. Aim for the wings, aim for the fuselage center. Anywhere fuel flows, the Betty burns. Tokyo, Imperial Japanese Navy Aviation Bureau, March 1943. Captain Minoru Genda read the loss reports from Rabaul with growing alarm. In February alone, the 4th Air Group had lost 47 Betty bombers to enemy fighters, nearly 80% of its operational strength. Crew casualties exceeded 400 aviators. Replacement aircraft were arriving, but experienced crews could not be replaced at sustainable rates. The pattern was repeating across every theater. At Wewak, New Guinea. 23. Bettys lost in a single week. Over the Solomons, entire formations shot down before reaching targets. Near Rabaul itself, bomber groups suffering 40–50% losses per mission. The tactical solution seemed obvious. Retrofit G4M bombers with self-sealing fuel tanks and armor protection, as American bombers universally incorporated. Genda requested a feasibility study. The response from Mitsubishi Heavy Industries arrived 2 weeks later. Chief Engineer Jiro Tanaka's report was blunt. Retrofitting existing G4M aircraft with self-sealing fuel tanks is not feasible given current material availability and industrial capacity. The problem was rubber. Self-sealing fuel systems required specialized synthetic rubber compounds, materials that swelled when exposed to aviation fuel, automatically sealing bullet holes. American manufacturers used neoprene-based formulations. British systems employed similar compounds. Both nations had developed synthetic rubber industries before the war. Japan had not. Japanese rubber supplies came almost entirely from natural sources, plantations in Southeast Asia, Malaya, and the Dutch East Indies. The Imperial Navy and Army competed for limited stockpiles. Tire production consumed the majority. Aircraft manufacturing received low priority. Even if rubber could be secured, the manufacturing infrastructure didn't exist. Self-sealing tank production required specialized facilities, trained workers, quality control systems, and supply chains that Japan hadn't developed. American factories produced self-sealing tanks by the thousands. Japanese industry struggled to produce them at all. Tanaka's report detailed the mathematics. Retrofitting a single G4M with self-sealing fuel systems requires approximately 180 kilograms of rubber compound, plus 320 kilograms of additional structural reinforcement. Current monthly rubber allocation to aviation sector, 840 kilograms total. This quantity could retrofit 4 aircraft per month against production output of 110 new G4M bombers monthly. The numbers made retrofitting impossible. But even if materials existed, the design changes would create new problems. Adding 500 kilograms of protection systems to an aircraft already operating at maximum weight would reduce range by approximately 600 kilometers, eliminating the Betty's primary advantage. Japanese doctrine depended on that range. Forward air bases were increasingly under attack. Operating from rear positions required bombers capable of striking targets 1,000+ miles away. A short-range Betty was strategically useless. Genda proposed designing a replacement bomber with integrated protection from the start. Mitsubishi's response: preliminary design studies would require 18 months, prototype development another 12 months, production tooling 6 to 8 months more. First operational deliveries, late 1945 at earliest. The Navy couldn't wait 3 years. Alternative proposals emerged and died quickly. Reduce bomb loads to save weight for armor? Unacceptable. Negated the bomber's offensive purpose. Reduce crew size? Already minimal. Install partial protection for critical areas only. Testing showed this provided negligible survivability improvement. Every option failed basic feasibility analysis. By mid-1943, Japanese commanders faced an impossible situation. The G4M's vulnerability was killing experienced crews faster than training could replace them. But industrial limitations, material shortages, and strategic requirements trapped the Navy in continuing operations with an aircraft everyone knew was fatally flawed. Captain Genda's final memo to the Aviation Bureau in June 1943 acknowledged the reality. We will continue G4M operations with existing design. Tactical modifications, tighter formations, night operations, fighter escorts when available, will attempt to mitigate vulnerability. Material and industrial constraints prevent fundamental redesign. The Betty would fight on unchanged, and crews would continue dying in aircraft their own commanders knew couldn't protect them. April 18, 1943. Skies over Bougainville, Solomon Islands. Admiral Isoroku Yamamoto's itinerary was precise. Depart Rabaul at 0600 hours, arrive Balale Airfield at 0800 hours, inspect forward positions, return by afternoon. 2 Betty bombers would carry the Admiral and his staff. 6 Zero fighters would provide escort. American cryptanalysts at Station Hypo, Pearl Harbor, had decrypted the schedule 3 days earlier. At Kukum Field, Guadalcanal, 18 P-38 Lightning pilots received their briefing at 0530 hours. Major John Mitchell commanded the intercept mission. Captain Thomas Lanphier would lead the attack element. The target? Admiral Yamamoto himself. He'll be in one of 2 Betty bombers, the intelligence officer explained. 6 Zero escorts. Your window is approximately 2 minutes over Bougainville's southwest coast. The P-38s departed at 0725 hours, flying low over the ocean to avoid Japanese radar. Mitchell navigated by compass and dead reckoning across 435 miles of open water, a flight profile that only the P-38's extended range made possible. At 0934 hours, Mitchell spotted the Japanese formation exactly where intelligence predicted. 2 Betty bombers flying at 4,500 feet, 6 Zeros stepped up above them at 6,000 feet. Bogies, 11 o'clock, Mitchell transmitted. Attack element. Go! Lanphier and his wingman, Lieutenant Rex Barber, broke left, accelerating toward the bombers. The remaining P-38s climbed to engage the Zero escorts. The Japanese fighters dove immediately, but Lanphier had altitude and speed advantage. He closed on the first Betty, Yamamoto's aircraft, from the left rear quarter. At 300 yards, he opened fire. The P-38's armament, 1 20mm cannon and 4 50-caliber machine guns concentrated in the nose, delivered devastating hitting power. Lanphier's burst lasted approximately 2 seconds. Rounds stitched across the Betty's left wing. The fuel tanks exploded instantly. Not a progressive fire, not smoke followed by flames. An instantaneous explosion that consumed the entire wing in a fireball visible from 10 miles away. The bomber's left wing separated from the fuselage. The aircraft rolled inverted, still burning, and plunged into the jungle canopy below. From first hit to impact, less than 4 seconds. There were no parachutes. Rex Barber engaged the second Betty simultaneously, his guns tearing into the bomber's fuselage and right engine. That aircraft caught fire more gradually but no less catastrophically, flames spreading from punctured fuel lines throughout the wing structure. The Betty crashed into the ocean off Moila Point. The entire engagement lasted fewer than 5 minutes. Japanese search teams reached Yamamoto's crash site the following morning. They found the Admiral's body still strapped in his seat, thrown clear when the fuselage impacted. He had been killed by the crash, not by enemy fire, but the crash was inevitable the moment Lanfear's rounds punctured those unprotected fuel tanks. The irony was absolute. Yamamoto had championed Japanese naval aviation throughout the 1930s. He had supported the development of long-range bombers like the G4M. He had approved the design philosophy that prioritized range over protection. He understood the trade-offs, had personally reviewed specifications that eliminated self-sealing tanks to save weight. And on April 18, 1943, that design philosophy killed him. The Betty that carried Admiral Yamamoto was identical to the thousands of G4M bombers operating across the Pacific. Same thin fuel tanks, same unprotected lines, same deliberate vulnerability accepted in exchange for operational range. Lanfear's 2-second burst simply exposed what every American fighter pilot already knew. Hit a Betty's wing, it explodes. That morning, Japan's most important naval strategist died inside an aircraft that couldn't survive a short burst from modern fighters. The loss was catastrophic for Japanese morale. But the larger tragedy was this. Yamamoto's death changed nothing about G4M operations. The bombers continued flying with unprotected fuel tanks. Crews continued dying in identical circumstances. The design couldn't be changed, and the war had 2 more years to run. March 21st, 1945. Skies south of Kyushu, Japan. 18. Betty bombers lifted off from Kanoya Air Base at dawn. Each aircraft carried a modified payload, one Oka kamikaze rocket plane suspended beneath its fuselage. The Oka, called Baka, Fool, by American intelligence, was Japan's final desperate innovation. A piloted rocket bomb, 1,200 kilograms of explosives, 3 solid fuel rockets, and a human guidance system. Once released, the weapon would accelerate to 650 kilometers per hour, making interception nearly impossible. But the Oka had to reach release range first. That required the Betty bombers to survive within 23 miles of American naval forces, close enough for the rocket planes to glide to their targets after release. Lieutenant Commander Goro Nonaka commanded the mission from the lead Betty. At 41 years old, he was one of the most experienced bomber pilots still alive in Japanese naval aviation. He understood exactly what this mission demanded and what it would likely cost. The formation flew at 6,000 feet, heading southwest toward the American fleet off Okinawa. 30 Zero fighters provided escort, every available aircraft Kanoya could spare. At 11:30 hours, American radar on the picket destroyers detected the formation 65 miles out. Fighter direction officers scrambled every available interceptor. 50 F-6F Hellcats from carriers Essex, Bennington, and Hornet vectored toward the contact. They reached attack position at 11:47 hours. The Zeros fought desperately, but they were outnumbered nearly 2 to 1, and the Hellcat pilots were experienced, well-trained, and flying superior aircraft. The Japanese fighters couldn't stop what came next. The Hellcats tore through the Betty formation like sharks through a school of fish. Lieutenant Howard Rutledge locked onto a Betty from the port quarter. His 650 caliber machine guns ripped into the bomber's left wing. The fuel tanks ignited immediately, the familiar orange explosion every Pacific fighter pilot had seen dozens of times before. But this explosion was different. The Oka beneath the Betty's fuselage, packed with 200 kilograms of high explosives, detonated sympathetically. The combined blast was so massive it damaged 2 adjacent Bettys, which then exploded in their own cascading fireballs. 3 bombers destroyed in 4 seconds. All across the engagement zone, Bettys were burning. The Oka weapons made each aircraft a flying magazine. Any hit that ignited fuel would likely detonate the bomb beneath the fuselage as well. Nonaka's bomber absorbed fire from multiple attackers. Flames spread along both wings simultaneously. He attempted to release the Oka early, hoping to at least launch the weapon toward the distant American fleet. The release mechanism failed. The Oka remained attached as fire consumed the Betty's wing structure. The bomber rolled onto its back and fell, still carrying its wound 200-kilogram payload. The engagement lasted 12 minutes. All 18 Betty bombers were shot down. All 18 Oka pilots died, never launching, never striking, never even approaching their intended targets. Over 160 Japanese aviators killed. The 30 Zero escorts suffered heavy losses attempting to defend the formation. Not a single Oka reached release range. Not a single American ship was threatened. The mission achieved nothing except adding 180 more names to Japanese casualty lists. Commander James Ramage, leading the Hellcat squadron from Essex, described the engagement in his after-action report. The enemy bombers showed the same vulnerability observed throughout the war. Fuel fires spread instantly upon any wing hits. The additional explosive payload made each aircraft catastrophically unstable. Total formation destroyed before reaching attack range. The Betty's fundamental design flaw, unprotected fuel tanks, had ensured that Japan's most sophisticated kamikaze weapon never had a chance to prove itself. The bombers designed to carry it couldn't survive long enough to deliver it. By April 1945, with Okinawa secured and American forces preparing for mainland invasion, the G4M Betty remained in service simply because Japan had nothing to replace it with. The design that seemed brilliant in 1939 had become a death sentence by 1945. And still, the bombers flew. February 1945, Clark Air Base, Philippines. Major Frank McCoy's team had been documenting the captured Betty for 3 weeks. Every system, every component, every design choice that had seemed inexplicable from the outside now laid bare under forensic examination. The final technical report ran to 147 pages. McCoy sat in the makeshift intelligence office reviewing the findings, comparing them against captured Japanese engineering documents his team had recovered from abandoned facilities. The documents confirmed what the physical evidence had already revealed. Every vulnerability was intentional. The fuel system epitomized the design philosophy. The Betty carried 4,780 liters of aviation fuel distributed across multiple tanks in the wings and fuselage. Standard American practice would have protected this fuel with self-sealing bladders, armor plate around critical areas, fire suppression systems, and redundant feed lines. The Betty had none of these. Fuel tanks were simple aluminum shells, 2 to 3 millimeters thick, wrapped in fabric covering. No rubberized lining, no swelling compounds, no protective layers of any kind. A single 50 caliber round, penetrating anywhere in the wing, had direct access to thousands of liters of high-octane fuel. The feed lines were equally exposed. They ran along structural ribs with no protective sheathing, no redundant systems, no isolation valves that might contain fire to a single tank. Once fuel ignited in one section, it spread throughout the entire wing structure within seconds. McCoy's metallurgist examined the aluminum skin samples. "This is high-grade material," he reported. "Well manufactured, properly heat-treated. They didn't use inferior metal, they just used very little of it." The crew protection was similarly minimal. No armor behind pilot seats, no bulletproof glass in the canopy. The defensive gun positions offered gunners zero protection from return fire. A tail gunner sat completely exposed in a glass dome. Maximum visibility, zero survivability. The bomb bay showed the same weight-saving philosophy. Structural members were thinner than equivalent American bombers. Redundant supports were eliminated. Safety margins were reduced to theoretical minimums. Lieutenant Chen calculated the weight savings. Eliminating self-sealing tanks saves approximately 180 kilograms. Removing armor plate saves another 320 kilograms. Thinner structural elements throughout save perhaps 400 more kilograms. Total weight reduction, roughly 900 kilograms. And what does 900 kilograms buy? McCoy asked. Chen consulted the performance data captured from Japanese documents. Extended range of approximately 800 kilometers, or increased bomb load of 400 kilograms, or improved high-altitude performance. The trade-off was now undeniable. Japan had purchased range by selling crew survival. The captured engineering specifications made the philosophy explicit. One document, dated 1938, stated the design priorities clearly. Maximum range and speed are essential for offensive operations. Protective systems reduce performance and are therefore secondary considerations. Enemy fighter opposition is expected to be limited. That final assumption, limited enemy fighters, had proven catastrophically wrong. By 1942, American industrial capacity was producing fighters by the thousands. Hellcats, Corsairs, P-38s, P-47s, all fast enough, high-climbing enough, and numerous enough to intercept Betty formations routinely. The bomber's vulnerability, acceptable when facing limited opposition, became a death sentence when facing American fighter strength. McCoy's report concluded with an assessment that would be distributed throughout Allied intelligence. The G4M represents a coherent design philosophy that prioritized offensive capability over crew survivability. This approach succeeded during the war's opening phase when Allied fighter opposition was limited. Once American fighter strength increased, the design's fundamental vulnerabilities became catastrophically apparent. The enemy's inability to retrofit protection systems due to material and industrial limitations trapped Japanese forces in operating an aircraft they knew was obsolete. The captured Betty sat silent on the tarmac outside, a monument to calculated risk that failed. Every system documented, every choice explained, every vulnerability catalogued. Japan had built a bomber that could reach impossible distances. They just couldn't build one that could come back. The arc of obsolescence. The G4M. Betty bomber's combat history traced a perfect curve of diminishing returns. A weapon that achieved everything its designers promised, then collapsed under the weight of its own compromises. December 1941 through June 1942, the ascendant phase. Betty formations struck across the Pacific with near impunity. Clark Field, Force Z, Darwin, Port Moresby, Guadalcanal. The bomber's extraordinary range gave Japanese forces strategic reach no Allied commander could match. Loss rates remained minimal, typically below 5% per mission. Crews accumulated combat experience. Tactical doctrine evolved around the aircraft's capabilities. The design philosophy worked perfectly under these conditions. Limited Allied fighter opposition, dispersed defensive positions, vast distances that favored long-range bombers. Japan's pre-war assumptions about Pacific warfare appeared validated by 6 months of devastating success. Then the curve bent downward. August 1942 marked the inflection point. Guadalcanal. 18 of 23 bombers lost in a single engagement. The Betty's vulnerability, hidden when Allied fighters couldn't reach formations in strength, became catastrophically apparent once interception became routine. Loss rates climbed steadily, 15% per mission by late 1942, 25% by mid-1943, exceeding 40% by 1944. The mathematics were unsustainable. An air group suffering 25% losses per mission would be effectively destroyed after 4 sorties. Replacement aircraft arrived, but experienced crews, the men who knew the bomber's systems, who understood its tactical employment, who had survived previous missions, couldn't be replaced at rates matching losses. The Betty's tactical effectiveness collapsed in inverse proportion to Allied fighter strength. As Wildcats gave way to Hellcats, as P-40s were supplemented by Corsairs and P-38s, as American pilot training improved and numbers increased, Betty formations faced increasingly lethal opposition. By 1943, the bomber that had seemed invincible in 1941 became a liability. Missions required massive fighter escorts, resources diverted from other operations. Night operations became standard, reducing bombing accuracy. High-altitude approaches were abandoned for low-level strikes that decreased vulnerability to fighters but increased exposure to anti-aircraft fire. Nothing worked sustainably. The fundamental design couldn't be changed. Material shortages prevented retrofitting protection systems. Industrial capacity couldn't support crash development of replacement aircraft. Strategic requirements demanded continued operations despite known vulnerabilities. Japanese commanders found themselves trapped in a tactical death spiral, continuing operations with an aircraft they knew was obsolete, losing experienced crews faster than training could replace them, watching combat effectiveness deteriorate monthly. The statistics told the story brutally. From 1941 through 1945, Japan produced approximately 2,435 G4M bombers across all variants. Combat losses, accidents, and operational attrition consumed nearly 90% of production. By war's end, fewer than 150 remained operational. Crew casualties were even more devastating. Each Betty carried 7 to 9 men. Conservative estimates suggest over 15,000 Japanese aviators died in G4M operations. Pilots, navigators, bombardiers, gunners, radio operators. Men whose training took years, whose experience was irreplaceable, whose loss represented institutional knowledge that couldn't be recovered. The Betty succeeded brilliantly when success required only range and payload. It failed catastrophically when success required survival. The bomber was never designed to fight through 1945. It was designed to win by mid-1942, to achieve decisive strategic results before enemy fighter strength could develop, before American industrial capacity could fully mobilize, before the war's character transformed from offensive operations to defensive attrition. Japan's strategic timeline failed. The Betty's design timeline failed with it. By 1945, the aircraft was an anachronism, a weapon built for a war that ended in 1942, flying in a conflict it was never meant to survive. August 19, 1945. Ieshima Airfield, Okinawa. 2 Betty bombers approached from the north, their silhouettes unmistakable even at distance. But something was different. They were painted entirely white. Large green crosses marked their fuselages, the internationally recognized symbol of non-combatant aircraft. American fighters escorted them in tight formation, ensuring no overeager pilot mistook their purpose. The Bettys landed at 1400 hours, their wheels touching down on an airfield American forces had captured just 4 months earlier. The engines shut down. The hatches opened. 16 Japanese officials emerged. Diplomats, military officers, technical staff. They carried instructions from Emperor Hirohito to negotiate the formal terms of Japan's surrender. Lieutenant General Torishiro Kawabe led the delegation, his face showing the exhaustion of a nation that had fought to its absolute limit. American personnel watched silently as the Japanese delegation descended from the bombers. Many recognized the aircraft type immediately. 4 years of Pacific combat had made the Betty's distinctive profile unforgettable. These were the same bombers that had destroyed Clark Field in December 1941. The same aircraft that had sunk Prince of Wales and Repulse. The same bombers that had terrorized the Pacific theater for 6 months, projecting Japanese power across impossible distances. Now painted white, carrying surrender documents instead of bombs. The symbolism was lost on no one. Colonel Charles Tench, who'd survived the Clark Field raid in 1941, stood watching the Japanese delegation cross the tarmac. 4 years ago, I watched those things burn my entire squadron, he said quietly. Now they're bringing us their surrender. The Betty bombers that carried the delegation were among the last operational G4M aircraft in Japanese service. Most had been destroyed in combat, lost to accidents, or cannibalized for parts. These survivors had been selected for the surrender mission because they possessed the range to reach Okinawa from mainland Japan, the same capability that had made them formidable in 1941. But that range had cost Japan dearly. The design philosophy that prioritized reach over protection had consumed thousands of aviators, gutted entire air groups, and ultimately failed to achieve the strategic objectives it was meant to enable. The two White Bettys remained at Ieshima while the delegation flew to Manila for detailed surrender negotiations. They sat on the tarmac, unarmed, non-threatening, symbolic of a war Japan could no longer sustain. On August 28th, after surrender terms were finalized, the delegation returned to the waiting bombers. The aircraft departed northward, carrying documents that would end the Pacific War. The Betty's operational history had come full circle. The bomber that opened hostilities by striking American airfields now closed them by carrying surrender delegations. The aircraft designed to project Japanese power across the Pacific now symbolized that power's complete exhaustion. In the end, the Betty achieved exactly what its designers intended. It reached impossible distances, struck targets no other bomber could hit, and demonstrated capabilities that seemed to validate pre-war doctrine. But those achievements came at a price Japan couldn't sustain. The same design choices that enabled the Betty's range ensured its vulnerability. The same philosophy that made early victories possible guaranteed later catastrophic losses. Major Frank McCoy, reviewing intelligence summaries from Okinawa, noted the surrender mission in his final report on the G4M program. The aircraft that symbolized Japanese offensive capability in December 1941 concluded its service symbolizing Japanese defeat in August 1945. The evolution reflects not just technological or tactical failure, but the collapse of the strategic assumptions that shaped the Betty's design. It was a bomber built to win quickly, employed in a war that lasted far too long. The White Bettys flew into history, and with them went the final chapter of a design philosophy that had traded crew survival for range, protection for performance, and ultimately, victory for reach. The gamble failed. The crews paid the price, and the bombers that survived carried the admission of defeat.